Hello my dear children, once again welcome to our physics class. Hope you all are fine over there. Children, in the previous session we had discussed about angular acceleration. Also we discussed about the relationship between torque and angular acceleration. We also derived a relation for kinetic energy of a rotating body. I hope you remember all those expressions very well. Today let's discuss about angular momentum in case of rotation about a fixed axis. When a rigid body is rotating about a fixed axis, what will be the expression for the angular momentum of that rigid body? So for that we need to consider a rigid body. Let this be the axis of rotation, and a rigid body like this is rotating about this axis. And inside the rigid body so many particles are there, and we are considering 3 such particles inside the rigid body for our convenience. So let this be the first particle. Mass of that particle, let it be m1, and let its distance from the axis of rotation be r1. Consider another particle here. Let it be m2. Let its mass be m2. And let its distance from the axis of rotation be r2. Now consider another particle, a third particle here, and let its mass be m3, and let its distance from the axis of rotation be r3. Okay, so here we can assume that v1, v2 and v3 are the linear velocities of these particles. v1, v2, v3 are the linear velocities of this particle. So what will be the linear momentum? Even though the particle is executing a rotational motion, linear velocities will be acting on this particle, which will be tangential to this circular path or to the rotational path. Okay, so the momentum, linear momentum P1 of the first particle is m1v1, and we had already studied an expression relating linear velocity v and angular velocity omega, that is v is equal to r omega. So v1 will be equal to r1 omega. So m1v1 will be equal to m1 r1 omega. Similarly, linear momentum of the second particle P2 is equal to m2 into v2, that is equal to m2 r2 omega. And linear momentum of the third particle is m3 into v3, that is equal to m3 r3 omega. No need to write omega 1, omega 2, omega 3 like that, because the rigid body is rotating about the axis with a constant velocity, angular velocity omega. So all the particles inside that rigid body will execute the same angular velocity omega. Okay. And we had already studied the expression for angular momentum of the particle inside the rigid body. So this is the expression: angular momentum L is equal to P cross R, or P is the linear momentum and R is the radius. Okay. So angular momentum of the first particle will be P1 cross R1. And what is P1? From here we will get the expression for P1. P1 is equal to m1 r1 omega cross r1. Okay, and that is equal to m1 r1 square omega. Similarly, angular momentum of the second particle L2 will be equal to m2 r2 square omega. Okay, so what will be the total angular momentum of the rigid body about the given axis? So total angular momentum is equal to L1 plus L2 plus L3. Now if there are n particles, it can be generalized as plus Ln. So the total angular momentum L is equal to, what is L1? L1 is m1 r1 square omega plus L2 is m2 r2 square omega plus etc. plus mn Rn square omega. Okay, so this is the total angular momentum, and from this we can generalize this expression like this, or we can simplify this expression like this. Omega is a common factor. When we take omega as a common factor, we are left with m1 r1 square plus m2 r2 square plus etc. plus mn Rn square. Okay, so what are the terms inside the bracket represent? This terms represents the total moment of inertia of the rigid body, because m1 r1 square will be the moment of inertia of the first particle, m2 r2 square is moment of inertia of the second particle, mn Rn square is moment of inertia of the nth particle. So the sum of moment of inertia of all the particle represents the total moment of inertia of the rigid body. So we can write L is equal to omega into I, because the terms in the bracket represent moment of inertia, total moment of inertia of the rigid body. So we can write total angular momentum L is equal to omega I. Again we can rearrange that. We can write I in the beginning and omega later. So what will be the total angular momentum expression? It will be I omega. Okay, so I omega is also an expression for the total angular momentum of a rigid body about a fixed axis, rotating rigid body about a fixed axis. Okay, so L is equal to I omega. Now, what is the conservation of angular momentum? So conservation of angular momentum states that in the absence of external torque, total angular momentum of a body or a system of bodies are constant. So we had already studied in the absence of force, that means if external force is 0, then total linear momentum is equal to a constant. So similarly, if external torque is 0, then the total angular momentum will be a constant. So this is the conservation of law of conservation of angular momentum. In the absence of external torque, the total angular momentum of a body or a system of bodies are a constant. So we had already studied one expression relating torque and angular momentum. What is the expression? Torque tau is equal to dl by dt, isn't it? So here in this expression, if torque tau is equal to 0, you will get dl by dt is equal to 0, and dl by dt equal to 0 implies dl equal to 0. dl means what? dl is the change in angular momentum. Change in angular momentum is equal to 0, which means there is no change in angular momentum. That is, angular momentum L is a constant. Okay, so this is law of conservation of angular momentum. If L is constant, we had studied that L is equal to I omega. So in the absence of external torque, this I omega is also a constant. Okay. Now what are the applications of law of conservation of angular momentum? So the first application is, if the polar ice cap melts, the length of the day increases. How we can explain this concept with respect to the law of conservation of angular momentum? See, you know, Earth is a rotating body, so it has got an angular momentum, and angular momentum of the Earth is constant. So for Earth, angular momentum L is equal to I omega is a constant. And when the polar ice cap melts, what will happen? See, this is Earth, this is the polar region, this is the equatorial region. So when the polar ice cap melts, water will flow from polar region to equatorial region. So more water will get accumulated on the equatorial region. So the mass concentrated on the equatorial line will be more. When the mass concentrated is more, moment of inertia I is equal to mr square. So if mass increases, then moment of inertia I also increases. Okay, and if angular momentum L is to be constant, if I increases, then omega should decrease. Then only angular momentum L can be a constant. And you know the angular momentum of the earth is a constant. So if it is to be a constant, if I increases, omega should decrease. So here when the polar ice cap melts, water will flow from polar region to equatorial region, which increases the moment of inertia of the equatorial line. If moment of inertia increases, consequently omega should decrease. Omega is the angular velocity. It should decrease in order to keep the angular momentum of earth a constant value. So if omega decreases, what does it mean? The rotational speed of the earth decreases. That is, earth rotates slowly. If earth rotates slowly, the length of the day will increase. That will be the consequence, isn't it? Because the time taken by the earth to complete one rotation will be more. So what happens? That the length of the day will increase. Only when earth completes one rotation, one day is over, isn't it? So length of the day will increase when the rotational speed of the earth decreases. So that is the first application. Now what is the second application? If the earth loses its atmosphere, the length of the day decreases. So why is it so? Again earth, so the angular momentum of earth is a constant. Now for earth, there is no torque acting on it, hence angular momentum is constant. When earth loses the atmosphere, moment of inertia will decrease. Why? Because the mass concentrated will decrease when earth loses its atmosphere. So if moment of inertia decreases, consequently omega should increase. That means angular speed should increase. Angular speed increases means what? The earth quickly completes its rotation. So the length of the day decreases. Okay, just reverse of the first application. Then what is the third application? Motion of a girl standing on a turntable. So you might have noticed, if a girl is rotating with a uniform speed on turntable, its angular momentum will be a constant, provided she should rotate with uniform speed on the turntable. So its angular momentum will be a constant, and when she suddenly stretches her hand, what happens? I increases. Why? See, when she suddenly stretches her arms, this is the axis of rotation. She is rotating about this axis, and her distance from the axis of rotation is increases. Okay, this is the distance from the axis of rotation, that is I increases. R increases. So you know R is equal to mr square. So this R is increasing. When R increases, moment of inertia I also increases. So moment of inertia I is large in this case. And again, if moment of inertia is large, consequently omega should be less, isn't it? So omega should be less. Omega should be less means what? The rotational speed will be less. So if the girl stretches her hand, moment of inertia increases and the rotational speed decreases. So if she stretches her hand, her rotational speed decreases. But at the same time, when she withdraw her hands, what happens? When she brings her hands close together, what will happen? Yeah, this R will decrease now, because this is the axis of rotation and R is less now. So consequently moment of inertia I will be less. If moment of inertia is less, then omega should increase. So the rotational speed will increase. So the girl standing on a turntable rotates with greater speed if she brings her hands close to each other, and at the same time the rotational speed of that girl decreases when she suddenly stretches her hands. Okay. Now you can see a circus acrobat and a diver also take advantage of conservation of angular momentum. See here, the diver, while leaving the springboard, is throwing himself in a rotating motion. When he brings his hands and legs close, like this, what happens? Its moment of inertia will decrease and omega will increase. So speed of this boy is increasing now. But before reaching water, you might have noticed, he suddenly stretches his hands and legs. See, because when he suddenly stretches his arms and legs, moment of inertia increases and omega decreases, so that he gets a smooth entry into the water. Omega decreases means what? Angular velocity decreases. So he can smoothly enter into the water. Okay, so conservation of angular momentum is behind it. Okay children, so these are some of the applications of angular momentum. So with this I am concluding my session. I am concluding this chapter too. Notes of the topic and YouTube video have been uploaded. Just go through it. We will meet in the next session. Till then, take care all of you. Stay home, stay safe. Thank you.